All right, good afternoon, class. I'm here with Hazel again. And we're going to teach you some physics today. Let's see, what was I going to say? Um, hey, Ava. Hey, Matthew. Um, I wanted to let you guys know. Hey, Elena. Hey, Sebastian. One thing I wanted to let you guys know is I'm giving you guys the day off tomorrow. Um, so there's going to be no lesson tomorrow. Um, and the reason for that is that this is kind of the last lesson of content that is on the AP Physics 1 exam. Next week, I will be reviewing for the AP exam. And so there will be a quiz next week on this week's topics. But then for about 2 weeks or so, we're not going to have any quizzes because I'm going to assume that you're studying for the AP Physics 1 exam. We'll still have homework because basically what I'm going to be doing is AP practice problems where I'll spend my lesson doing an AP practice problem, then I'll give you guys an AP practice problem, and then we'll just so your daily items will be AP practice problems for the next few weeks until the AP exam. Hey, Brenna. Let's see. Another bit of news, I received my government stimulus check. And so I'm going to be, and I figure if I'm trying to stimulate, if it's a stimulus check to stimulate the economy, the responsible thing to do is to spend that money. So I'm going to be getting some Crocs shoes. I want some Crocs. So let me know what color Crocs you think I should buy. I'm also going to get a throwing axe because I'm just good at throwing axes and I think it's fun, and I don't have one. And I really want to get into like metalworking, so I'm trying to figure out what I need to buy to get into metalworking. But yeah, so that's where I'm at. All right. Lightning McQueen Crocs. Why does everyone say pink Crocs? That's what they said last period too. Okay. Buy a Lego Death Star. I'm sure that my stimulus check is not going to be enough to buy that. Legos are too expensive. Okay. So today what we're going to talk about is gravitational potential energy. So this is the last topic. So I actually so remember the formula for gravitational potential energy. It's U equals mg y. I'm not sure I want to be a pretty princess with pink Crocs, Charlotte. Okay, so I'm going to get to physics now. So this is the formula for gravitational potential energy. And if we were to graph gravitational potential energy versus elevation, you can see that it depends on y to the first power. So this is actually going to be a straight line. Okay. And you can see the slope of that line is mg. But here's the problem. The problem is that now this formula, recall that gravity actually gets weaker the farther away from a planet you get, okay? And so we use this formula like the line just continues forever and ever and ever, okay? But in reality, because gravity gets weaker, as you get to really, really high elevations, gravity gets weaker, and so this starts to level off. And it turns out that there's sort of a maximum gravitational potential energy that you can get because gravity weakens. All right? So there's a maximum gravitational potential energy you can have because gravity gets weaker. So, yeah, this graph actually, it plateaus. This equation is perfectly good. Use this equation near the Earth's surface. Okay? This equation is perfectly good near the Earth's surface. But if you have something like a satellite that's going way far out and then coming way back, then you got to use the other equation. So I'm going to tell you the real equation for gravitational potential energy, which is U equals negative G M1 M2 over R. It's windy. So this is the real equation for gravitational potential energy. It has a more complicated form than this one, but it's more accurate. So if you can get away with it, use this one. Otherwise, you got to use this one. So, people who are designing airplanes are flying close to the Earth's surface. They can get away with this one. But if you're going to work for NASA, where something's going way far away from the Earth's surface, you got to use this one. Okay. So, M1 is the mass of the central body. M2 is the mass of U, basically, and R is the distance from the center of the planet. Okay. So what if we were to graph U versus R? All right. One of the weird things about this is that the graph is going to be negative. See how there's this minus sign here? So what the graph looks like is this. So notice how it has the exact same shape as this graph. But what they like to do is they've just taken this graph and they've shifted it down so that the maximum gravitational potential energy you can have is 0. So the maximum gravitational potential energy you can have is 0, and then it's just negative the closer you get. Why do they do that? It turns out that you can add a constant to the energy. As long as you add it to all the different types of energy, it makes no difference, right? What matters is energy differences. All right? So if you, for example, if you have 10 and 17, the difference between them is 7. But if I add 5 to both numbers, I get 15 and 22. The difference is still 7. So as long as I add or subtract the same amount from all the different types of energy, then it's okay. So what they do is they just subtract a constant from the gravitational potential energy so that the maximum is 0. Okay? So there you have it. So that's the real equation. I have seen some multiple choice questions on the AP exam that want you to know this formula. So let me show you how to use it. What if I have a number of planets? So what if I have planets here, 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 and here? Okay, where this distance right here is 3. This distance right here, 3 meters. This distance right here is 4 meters. Okay. And then let me give these masses. This is a 1 kilogram mass. This is a 5 kilogram mass. This is a 2 kilogram mass. And this is a 4 kilogram mass. Okay. And what if I want to know what is the total gravitational potential energy of this system? Okay. We're going to use this formula, but this formula applies to each pair of masses. Okay. So how many pairs of masses are there in this? If you have 4 masses, how many pairs can you make? Well, you could, this mass compare with this guy, it compare with this guy, or it compare with this guy across the center. Okay. Similarly, this mass can compare this way, it compare that way, or it can compare across the center. So the number of pairs you can make is 1, 2, 3, 4, 5, and 6. There's 6 pairs. So our gravitational potential energy is going to have 6 terms. And for simplicity, we're going to use big G equals 1. So we're going to assume it's a different universe from ours. We cranked it so that big G is equal to 1. Okay? So I'm going to have 6 terms. The first term would be maybe this pair. So the formula is negative G M1, which is 1, M2, which is 2, over R, the distance between these two, which is 3. Okay? Now let's do this pair. We have negative G times M1 times M2 over the distance between them, which is 4. Right, because this is 4, it's a rectangle. And then we have, let's do this pair. Negative G times M1 times M2. So 5 times 4 over R, which is 3. And then I'll do this pair. Negative G times M1 times M2 over R, which is 4. And then I have 2 more terms. It's the diagonals. And I made this a 3, 4, 5 triangle so that this distance right here is 5, just to make it easy. Negative G times M1, which is 1, times M2, which is 4, over 5. And then The last pair is this one, negative g times m1 times m2 over r. Okay, so now I want to add all those up. So looks like we have, this is 0.7, this is 1.3, I'm just rounding here. This is 20 over 3, that's 6.7, this is 2, this is 0.8, this is 2. So it looks like we have 2, 4, 6, plus 6 is 12, plus 1.5. So we have negative 13.5 joules is the total gravitational potential energy of that system. All right? If there were more masses, so maybe there were 5 masses, there would be more possible pairs. If there are less masses, then there are fewer possible pairs. What if you had a triangle of masses? How many pairs could you make there? Well, there would be 3 possible pairs, that one, like that. Okay? One more thing about gravity that I'm putting into this lesson. You'll notice, remember the gravitational force is big G m1 m2 over r squared. Okay? The mass that appears in the law of gravity, that is called the gravitational mass. Okay? It's called the gravitational mass because it appears in the law of gravity. If we consider Newton's second law of motion, F equals ma, the mass that appears in there is called the inertial mass. Because inertia is how you respond to forces. So it's called the inertial mass. So one of the things that is true is that your gravitational mass is equal to your inertial mass. And from the standpoint of Newtonian physics, there's no reason that they should be the same. There's no reason that your gravitational mass should be equal to your inertial mass. But what we found is that they are the same thing. Experimentally, we found that they are the same thing. And so the AP wants you to know the distinction between these two. Okay? It was only when Einstein came around, Einstein was able to answer this question of why gravitational mass is equal to inertial mass. And if you want to learn about that, you'll have to learn about Einstein's theory of relativity. So I'm not going to talk about that right now. Let me see. Let's look at the other comments here. Princess P, that's pretty funny. White Crocs with pins, that's a pretty good idea. Oh, thanks for the compliment, Alex. Looking ripped. All right. So I guess that's all I have for today. And I'll see you Monday. There will be a news broadcast Monday about sort of the plan for the AP studying. Okay. Layla asks, what are we going to learn about when the AP exam is done? Whatever I feel like. So probably it's going to be topics from the SAT physics, because I know some students who are juniors or in Layla's case, a sophomore, will want to take the AP Physics subject test at some point. So I'll try to prepare you for that. All right. So this is goodbye from me and Hazel until Monday. Bye now. Thanks for watching.